Hello everyone. Hope you are doing very well. As you all know that today we are going to cover the theory part 10 of our chapter Haloalkanes and Haloarenes. So let's start with our topic. NCRT chapter 6 Haloalkanes and Haloarenes theory part 10, and specifically today we are going to cover the section 6.7.2. This is disclaimer. Objective of today's lecture. After attending this lecture, you will be able to correlate the structures of haloalkanes and haloarenes with various types of reactions. So, we are going to see the reactions and the structure relation of haloalkanes and haloarenes with them. The topics that we are going to cover according to NCRT, first of all, the section, or you can say subsection 6.7.2, reactions of haloarenes. And then we will practice an in-text question 6.7. So let's begin with reactions of haloarenes 6.7.2 topic. Reactions of haloarenes. Haloarenes means aryl halides. Okay, benzene ring attaching with the halogen group. The reactions of haloarenes are divided into the three major categories. What are those? The first one is nucleophilic substitution reaction, where we use a nucleophile and the reaction occurs. Okay, so the first category which the haloarenes show is nucleophilic substitution reaction. Along with that, the second category is electrophilic substitution reaction, and the third category is reaction with the metals. Okay, so these are the three major categories in which you can divide the reactions of haloarenes majorly. Okay, today in this lecture we are going to cover specifically the nucleophilic substitution reactions by haloarenes. So nucleophilic substitution reaction, where nucleophile is going to attack on the haloarenes, okay, and the reaction proceeds. So aryl halides are extremely less reactive towards the nucleophilic substitution reactions compared to the alkyl halides. So comparatively to the alkyl halides, which are you can say alkyl halides means simple alkyl group connecting with or bonding with the halogen. Okay, comparative to those in the aryl halides, the nucleophilic substitution reactions is extremely lesser reactive. Okay, so we have some reasons regarding that why this happens, that aryl halides show a less reactivity towards the nucleophilic substitution reaction. The reasons for its low reactivity, first of all, the resonance effect. As you all know, we are talking about aryl halides, that means a presence of benzene ring should be there, right? Benzene ring have this resonance effect. Okay, so due to the presence of lone pair present on the halogen, okay, so we are talking about aryl halide, benzene ring attaching with the halogen, right? On the halogen there are lone pair present which participates in the resonance with the benzene ring, due to which the benzene ring shows the resonance effect. Okay, so this lone pair present on this halogen attaching with the benzene ring participate in the resonance with the benzene ring and shows the resonance effect. And due to this, a partial double bond character is built up in the carbon and the chlorine bond, or you can say in the carbon and the halogen bond. Okay, so we will see an example where we will see a benzene or over which a chlorine is present. So chlorobenzene example we will see. That's why we are mentioning here that carbon chlorine bond is of partial double bond character. Okay, why? Due to the presence of resonance effect, due to this lone pair of the chlorine participating in the resonance with benzene ring, due to which the partial double bond character arises in the carbon chlorine bond. And what will happen? As you know that double bond is stronger than the single bond. Okay, so bond becomes stronger. Still we have a partial double bond character, but comparative to that single bond, due to that partial double bond character acquired by the carbon chlorine bond, the bond will become stronger and harder to break. Now, if you want to attack the nucleophile on the carbon, which is holding the chlorine or the halogen, chlorine should be removed from there, right? But due to this resonance effect, due to which the partial double bond character arises, due to which the bond of the carbon and chlorine become stronger, and it is very hard to break it. So let's see the example of resonance effect in the chlorobenzene. So we have this chlorobenzene ring or structure where benzene ring is bonding with the chlorine halogen. And you can see these dots which are representing the lone pairs on the chlorine atom, right? What will happen? These lone pairs is going to participate in the resonance with the benzene ring, and this arrow you can see showing the direction of movement of these lone pairs. So these lone pairs of chlorine will go over this carbon to which the chlorine is attached, okay, due to which a partial double bond character arises between the carbon chlorine bond. Okay, so this, due to the partial double bond character, this double bond will break, okay, and the double bond electrons which are sharing, this charge will go over the next carbon. So here negative charge is coming and here positive charge is coming because its electron pairs just shifted from the chlorine to the benzene ring. Okay, so positive charge is coming on the chlorine and a negative charge is coming here on this carbon, because this here it was double bond present and the charge is shifted to this carbon, so negative charge. Now again this shifting happens, so this negative charge will again go at this carbon, and this double bond, due to the shifting of negative charge here, this double bond breaks and present as a charge over this next carbon. So you can see you will get this structure where chlorine is having a partial double bond character with the carbon, and due to the shifting of this negative charge over this carbon, here comes a double bond, and this double bond is present on this carbon as a negative charge, as a charge of electrons. So either here the negative charge is present. Now again the shifting of electron or the charge will happen. This negative charge again go over this carbon, and this double bond sharing electrons will go as a charge on this carbon, and you will get a this structure where negative charge is here and here we have a double bond. Okay, now again if you move one further more step, what will happen? This negative charge will go over this carbon, due to which this double bond, partial double bond character breaks out, and the charge or the electron that is sharing between the chlorine and carbon will go again as a lone pair on the chlorine, and you will get the exactly the first structure like structure. Okay, so this is a chain, or this is, you can say, this is a resonance effect you can observe when a chlorine atom is bonded with the benzene. Okay, so as I said, resonance effect in the chlorobenzene is described in this image step by step, and you can see clearly that there is a partial double bond character in the carbon chlorine bond, due to which this bond become stronger and it becomes very hard to break it for the attack of the nucleophile. Okay, so this is one of the reason that why aryl halides show extremely less reactivity towards the nucleophilic substitution reaction as compared to alkyl halides. In the alkyl halide, there was no resonance effect as effective as in benzene ring, right? Second reason of the low reactivity is difference in the hybridization of carbon atom in the carbon halogen bond. Also, in the carbon halogen bond, if you compare the hybridization of carbon atom, there is difference in the alkyl halide and the aryl halide. So if you see the hybridization in the aryl halide and alkyl halide, it is this. You can see in this diagram, we have this aryl halide, halogen connecting with benzene ring. The carbon here is acquiring a sp2 hybrid carbon. Okay, so hybridization of this carbon is sp2. Meanwhile, in the alkyl halide, the carbon at which the halogen is present having a hybridization sp3. So this is a sp3 hybrid carbon. Okay, so what will happen? sp2 hybrid carbon, that means you have a more s character comparative to sp3, right? So S character is more in the sp2, due to which there is more electronegativity, and due to which the electron is, or you can say electron pair of the carbon halogen bond is holding more tightly as compared to the alkyl halides, right? So if you compare between the haloarenes and haloalkanes, first of all, in the haloarenes, the carbon is sp2 hybridized carbon at which the halogen is present. Meanwhile, in the haloalkanes, the carbon is sp3 hybridized carbon. Now, what will happen due to the different hybridization of the carbon acquiring a halogen bond? First of all, S character will differ. In the haloarenes, there will be more S character, and in the haloalkanes, we have lesser S character because the hybridization is sp3. Okay. In the haloarenes, due to the more S character, the electronegativity is more. So, carbon will be more electronegative compared to the carbon which is present in the haloalkane, which is less electronegative. Now, what will happen in the haloarenes, due to the greater electronegativity comparatively, the electron pair will be held more tightly. And in the haloalkanes, it is reverse, that electron pair will be held lesser tightly because of its lesser electronegativity comparatively to the haloarenes. Now, in the haloarenes, now the bond pairs are holding more tightly. That means the bond will become stronger and the bond length will become shorter, right? So, it is interrelated. So, more S character, more electronegativity, due to which the electron pair will be held more tightly by the halogen, due to which the bond length will be shorter and the bond will be stronger. Stronger bond means you need very large energy to break it. So, it is difficult to break. Meanwhile, in the haloalkanes, we have lesser S character, due to which there is lesser electronegativity, due to which the electron pair are holding by lesser force. That means lesser tightly comparatively to haloarenes. Due to which, in the haloalkanes, the bond length will be longer and the bond will be weak. That means, comparative to haloarenes, the bond is easy to break in the haloalkanes. Okay. So, due to this difference, there is lesser reactivity towards a nucleophilic substitution reaction shown by haloarenes comparative to haloalkanes. Due to all these, reasons. Okay. Due to the difference in hybridization, due to the strong bond in the haloarenes, they show lesser reactivity towards the nucleophilic substitution reaction because the bond is stronger. So, you need higher energy or to break that bond. So, it is difficult to break the bond of carbon halogen to attack, the nucleophile. So, basically, for the nucleophile to attack on the carbon at which halogen is present, it is difficult in the haloarenes because the bond is stronger due to the more electronegativity or sp2 hybridization of the carbon. Third basic reason or third major reason is instability of phenyl carbocation. So, what will happen? The SN1 mechanism is ruled out in the haloarenes. Okay, SN1 mechanism is what? Remember, substitution nucleophilic unimolecular. So, this is first order reaction. This reaction happens in the two steps, where first step involves the carbocation formation and it is the rate determining step, where the rate is dependent upon the alkyl halide concentration, right? So, in the phenyl carbocation is unstable, due to which the SN1 mechanism is ruled out in the case of haloarenes. So, in haloarenes, they don't show SN1 mechanism. The reason behind is this is that self-ionization results in the formation of phenyl carbocation. So, what will happen? There is a self-ionization happening. Okay, what will happen? The positive charge, when the chlorine, or you can say when any halogen which is present on the carbon will removed, there will be a positive charge coming on the carbon, which will not effectively stabilize by the aromatic ring. Okay, so there is a formation of phenyl carbocation due to the self-ionization, and the phenyl carbocation is highly unstable and does not stabilize by it, even does not stabilize by the resonance. Okay, why is it so? So basically, in the phenyl cation or in the phenyl carbocation, the delocalization of that positive charge which is present on the carbon disrupt the aromaticity of the ring, due to which this making it energetically unfavorable. This is energetically unfavorable and does not stabilize by resonance. So your phenyl carbocation that you are getting after the removal of halogen is highly unstable. So when you take a chlorobenzene and it undergoes a self-ionization process, this is a phenyl carbocation you are getting, which is highly unstable. And even this is not stabilized by resonance also. Okay. So due to this, because your carbocation is unstable, you can't follow the SN1 mechanism, because SN1 in the SN1 mechanism, the carbocation stability is the key factor on which the reactivities depend upon, right? Fourth reason, due to the fourth reason for the lesser reactivity towards nucleophilic substitution reaction of haloarenes is repulsion. Electron-rich nucleophile is repelled by the electron-rich benzene ring. Okay, so electron-rich nucleophile which is coming towards the haloarenes is repelled by the electron-rich benzene ring. So it is less likely to attack the electron-rich nucleophile on the electron-rich benzene ring. The reason behind this, that due to the repulsion between the electrons of nucleophiles and the benzene ring, this happens. Okay, so benzene ring have the benzene ring is electron rich, and the nucleophile which is coming to attack over it is also electron rich, and due to the electron and electron present on the both side, we have this repulsion force in between. And due to the repulsion of electrons, or due to the repulsion between the electrons of nucleophile and the benzene ring, the repulsion factor arises, due to which, and this is one of the factor due to which the haloarenes show lesser reactivity towards this nucleophilic substitution reaction. Okay, so those were the major factors, that is why the haloarenes are showing lesser reactivity towards nucleophilic substitution reaction. Okay, I hope you have understand all. Now let's take the case of replacement of halogen, the halogen present on the benzene ring. So let's say chlorobenzene can be replaced under high temperature and pressure. Okay, so in the chlorobenzene, the chlorine which is attaching to the benzene ring can be replaced under high temperature and pressure condition. So if you provide higher temperature and pressure, that means it will not, like chlorobenzene chlorine cannot be replaced under the standard condition. So you have to apply the high temperature and pressure for the replacement of chlorine. So this is known as dose process that we are going to see, where you are taking a chlorobenzene. Okay, you are treating it with sodium hydroxide first of all under a very high temperature 623 Kelvin and high pressure, that is 300 atmosphere. Okay, and also you are treating it with a proton, so that you are getting your product as phenol. So this chlorine will be removed under the very high temperature and pressure conditions. After the reaction with sodium hydroxide and the proton, you will get your final product as phenol. Okay, and this process of conversion of chlorobenzene under these special conditions into the phenol is known as dose process. Effect of substituents. Now, if your benzene ring have any substituents, then what will be the effect on the reactivity of nucleophilic substitution reaction shown by the haloarenes? Presence of an electron withdrawing group like NO2. Okay, you can also call electron withdrawing group as EWG for the shorter form or for the easier way to understand. If there is any electron withdrawing group present at ortho and para position specifically, this will increase the reactivity of haloarenes. Okay, here we are taking the example of electron withdrawing group like NO2. Okay, so if a nitro group, NO2 group is present at specifically ortho and para position in the benzene ring, this will increase the reactivity of haloarenes. Why? Because it is an electron withdrawing group. It will withdraw the electrons of the benzene ring, and the benzene ring is more available for the electron rich nucleophile to attack on. So you have this reaction where this is chlorobenzene, at the para positions we have chlorine and nitro group, right? At the para position we have nitro group and chlorobenzene is the same. Okay, you are treating it with sodium hydroxide and a little lesser temperature, 443 Kelvin. Okay, in the when there is electron withdrawing group, okay, we are doing the same reaction of the substitution or substitution of the chlorine, okay, substitution of halogen. But here an electron withdrawing group NO2 is present at specifically para position in the benzene ring. So the temperature you are needed for this reaction to occur is lesser comparatively. Okay, so you are treating this compound with NaOH in the 443 Kelvin temperature and then with proton, and you are getting a phenol, or you can say nitrophenol. Okay, so chlorine will be removed, OH hydroxyl group will be attached, and the NO2 will be remaining same. Here the electron withdrawing group is NO2. That means it will withdraw the electrons of the benzene ring towards itself due to its property, and the benzene ring will be more available for the attack of electron-rich nucleophile. What if we have two NO2 groups present at ortho and para positions respectively? Now, if you place two nitro groups, one at ortho and one at para positions, the reaction will occur with just warming. Okay, so the temperature you are needing for that conversion of the removal of the halogen from the benzene ring will need a lesser temperature now if there is two NO2 or two electron withdrawing group present at the ortho and para positions. So you can see we have this benzene ring where two NO2 groups are present. One is at ortho carbon, another is one at para carbon, and we have chlorine at the first carbon in the benzene ring. You are doing this reaction at with the NaOH, sodium hydroxide, and in the proton, and you are needing the temperature 368 Kelvin, which is more lesser. Okay, and you are getting your desired product where at the ortho and the para position we have NO2 group attached, and at the first position we have hydroxyl. So chlorine will be removed and the hydroxyl will be attached. OH group will be attached in the benzene ring, and this reaction is occurring with just warming of this compound you're reacting. Okay, so the presence of two electron withdrawing group increases the reactivity of this haloarene, okay, to convert it into a phenol after the removal of this chlorine at a lesser temperature, okay, or you can say just by warming it. Okay, so the presence of a nitro group or electron withdrawing group at ortho and para positions increasing the reactivity of the haloarenes towards the nucleophilic substitution reactions. Why? Because it is an electron withdrawing group, it withdraws the electron of the benzene ring, and your electron rich benzene ring will become available for the attack of the electron rich nucleophile. Now, if you have three NO2 groups present on the ring at ortho and para positions respectively, that means we have, other than one para position is occupied by the chlorine, two ortho positions left and one para position left. All three positions are occupied by the NO2 groups. If that is the case, then reaction will occur with simple shaking. So, if you take this compound where you have three electron withdrawing groups present at your ortho and the para positions, then you just have to do this reaction in the water and warm it. Just by shaking it, you will get your desired product after the removal of chlorine, after the breaking of carbon chlorine bond, which was initially very strong, right? But due to the presence of three NO2 groups, that means three electron withdrawing groups, this reactivity of this compound, this reactant, is increasing or is increased. That reaction is occurring only with simple shaking, okay, and you will get your desired product. So the reactivity is increasing as you are increasing the electron withdrawing group on the ortho and the para positions of the benzene ring. Okay, so you can think about this fact that you are not applying or you are not placing the electron withdrawing group at meta positions. Why is it so? Right? So we will discuss this also. Let's see the mechanism first. So electron withdrawing group stabilizes the intermediate carbon ion formed during the nucleophile attack. Okay. During the nucleophilic attack, the carbon ion that is forming as an intermediate is stabilized by the electron withdrawing group. How? Negative charge is delocalized onto the carbon atom that is bearing the NO2 group. Okay. So the negative charge that is going to delocalized on the carbons on which the NO2 group is present, and the resonance will happen. So if you understand structurally, so for the orthoisomer, where ortho at the ortho position we have NO2. So if we have ortho at the ortho position, the NO2 group is attached, and you have at the para position chlorine, and at the ortho position you have NO2, which is the electron withdrawing group. What will happen? The nucleophile will attack over the carbon which is present in the benzene ring at which the chlorine is attaching. Okay, so hydroxyl group, which is a nucleophile, is attacking on the carbon, and what will happen? This double bond electron will shift over this carbon which is bearing the NO2 group, right? So you will get this structure. This is an intermediate and this is a slow step. So you will get this structure where at this first carbon we have chlorine, we have hydroxyl. At the second carbon we have negative charge and the NO2 group. Okay. Now what will happen? The negative charge present on this carbon at which the NO2 group is present, this negative charge will shift here, and the double bond charge will shift as on this carbon. Okay. So you will get this structure, where at first carbon we have chlorine and hydroxyl, at second carbon we have NO2 and a double bond, and the double bond previously was shifted to this next carbon as a negative charge. Okay. Now again, what happened as a resonance? This negative charge will again shift to here, and the double bond, or you can say negative charge shift to the next carbon, and the double bond will shift to the next carbon as a charge. So the electron pair will shift as a charge and present as a negative charge here, and there is a formation of double bond between these two carbons. Okay, and you will get this structure. Now what will happen? This negative charge will go here and form a double bond with this carbon, and this chlorine along with its electrons will be removed from here. Okay, and you will got your final product. So this is an intermediate state where this resonance is happening, and you can overall show it with this structure. So equivalent to these, all steps are equivalent to this structure, where we are showing that the negative charge is delocalizing over the carbons, and the carbon at which the NO2 is present, and you got this intermediate. And after that, after the removal of chlorine, this is a very fast step, chlorine will remove and you will get your stable product as this, where at the para position we have hydroxyl and at the ortho position we have NO2 group, and chlorine, or you can say chloride ion, will be removed from the reaction. This is a fast step. Okay, so what is happening? The electron withdrawing group, that is NO2, is stabilizing the intermediate carbon ion, which is forming by the shifting of this or by the presence of this negative charge due to the shift of double bond electrons, right? So this electron withdrawing group is stabilizing the intermediate carbon ion formed during the nucleophile attack, and due to which the negative charge is delocalizing on the carbon atom that is bearing the negative charge, and you will get your product without any you can say this is a fast step. Okay, so without any disruption you are getting your final product, okay, after the removal of chloride ion. So this is for the orthoisomer case, okay, where at the ortho position we have nitro group. Now for the para isomer, where the nitro group is present at the para position. So when the nitro group is present at the para positions, then what will happen? The nucleophile, the similar case will happen, that hydroxyl group, that is a nucleophile which attack on this carbon, the double bond will break and the electron will be shared as a charge over this carbon, and you will got this structure. Now this negative charge will delocalize over the carbon at which the NO2 is present. Okay, So negative charge will come here at the carbon at which NO2 is present, and then again negative charge will delocalize by the resonance and go over this carbon, and then this negative charge will go here, form a double bond, and this chlorine will be removed, okay, from the reaction. So all these three steps is equivalent to this intermediate forming, which is showing that negative charge is delocalizing over the carbon at which nitro group is present at the para position. And then a fast step will happen where the chloride ion will be removed from the reaction, and you will get your desired product, where at the para position you have NO2, and at the first para position you have hydroxyl group. So after the removal of chloride ion, you will get your phenol product. Okay, so this is the case where where at the para carbon you have nitro group. Okay, so we have seen that when the nitro group or electron withdrawing group is present at ortho position, and then when it is present at para position. Okay, now when it is present at meta position, so as I said that we will understand that why we are not talking about the meta position acquired by the nitro group, right? Now let's see. So for the meta isomer where the nitro group is present on the meta group, no effect will be shown when the electron withdrawing group or nitro group is attached at the meta position. Why? What is the reason? The reason is negative charge does not localized on the carbon that is bearing the NO2 group. So where when the negative charge comes after the attack of nucleophile, okay, the carbon ion forms after the attack of nucleophile, that negative charge does not localized on the carbon atom which is bearing the NO2 group in the meta isomer case. So when the nitro group or electron withdrawing group is present at the meta position, at that carbon, at the meta position carbon, the negative group or negative charge is not localizing. You will better understand by looking at this step or process. Okay, so this is a meta isomer we have taken where the electron withdrawing group we are taking is NO2 and it is present at the meta carbon. Okay, so this is meta carbon, meta position carbon. This is meta position and this is meta position. This is ortho, and these two are para. They are equivalent. Okay, so you are placing a nitro group or electron withdrawing group at meta position. Okay, now let's see, the similar step will happen, that nucleophile will attack over this carbon, this double bond electron will shift here as a negative charge, you will get your carbon ion. Now this negative charge will delocalize to the carbons. Okay, so what will happen, the next negative charge is coming here at the para carbon. Okay, so it is not coming at the meta carbon. The negative charge is not localizing to the carbon, or you can say meta carbon. Okay, so you will get this second structure where this negative charge is present at the para carbon. Now again this negative charge will localize and you will get your negative charge at the ortho carbon, and then the final step will happen where all these three steps you can represent it through this intermediate, which is equivalent to this structure where it is showing that negative charge is delocalizing over the carbons and the benzene ring by resonance. And the final step, which is a fast step where chlorine will be removed as a chloride ion along with its electrons, and you will get your desired products, and your NO2 or electron withdrawing group is present at the meta position as it is, and chloride will be removed. But here what is happening, the electron withdrawing group is present in our benzene ring, but it is not helping to increase the reactivity of the haloarenes towards nucleophilic substitution, because it is not contributing in that mechanism. Okay, because the negative charge or a carbon ion that is forming during this reaction, that negative charge coming on the ortho carbon, that is not localizing on the meta carbon at which the electron withdrawing group is present, so it will not show its effect. So no effect will be shown by the electron withdrawing group when it is attached at the meta position, and you will get your product anyway, but NO2 is not helping you on increasing the reactivity of haloarenes. Okay, so that's why we haven't considered the meta isomer where at the meta position the electron withdrawing group is present. That's why we have said that if electron withdrawing group is present at ortho and the para position, then it is going to increase the reactivity of haloarenes towards this reaction, because the negative charge is localizing over the carbons at which the NO2 group is present, or the carbons that is bearing the NO2 group, and due to which NO2 group or electron withdrawing group shows its effect of uh, withdrawing the electrons from the benzene ring and make available the benzene ring for the attack of nucleophile more easily over the benzene ring. Okay, so this is the case. Okay, let's see an in-text question. In-text question 6.7. The question is, which alkyl halide from the following pairs would you expect to react more rapidly by an SN2 mechanism? Explain your answer. So you have given first, second, and third alkyl halide pairs. Okay, the first is this bromobutane, and this is isobromobutane. The second is isobromobutane, or this is, you can say, 2-bromo 2-methyl butane propane. Okay, 2-bromo 2-methyl propane. Third is, you can say, bromo. We have bromine at the first carbon, and the methyl is present now as a substituent in this chain. And you have this next pair, or you can say the pair where the bromine is present at the first carbon, but the methyl is present at the second carbon as a substituent. Okay, so you have these three parts of this question where you have given the alkyl halides pairs. Okay, you have to tell that which pair or which of the following pair expected to react more rapidly by the SN2 mechanism, and you also have to explain your answer. So you have given some time, try to solve it, and then we will see the answer. Okay, let's see. So let's see that SN2 reaction we know is proceeds via single step mechanism. It is a substitution nucleophilic biomolecular reaction, and it proceeds in a single step. So it includes a single step mechanism, and the rate of SN2 depends on the steric hindrance of alkyl halide. Because it is a single step, so nucleophile is going to attack on the carbon at which the halogen is present from the opposite side of that bond, carbon halogen bond. Okay, so steric hindrance is the factor on which the reactivity of SN2 reaction depending upon. So order of reactivity for SN2 is highest for the primary halide, then for secondary halide, and then for tertiary halide, because primary halide have lowest steric hindrance, which is going to cause, or which is going to increase the reactivity of the SN2 reaction, because nucleophile is going to attack on the carbon very easily because of no steric hindrance. Meanwhile, in the tertiary alkyl halide, we have very high steric hindrance present, due to which the reactivity decreases. It will be very difficult for the nucleophile to attack on the carbon in the case of tertiary alkyl halide. So for the comparison between the two molecules, check it is primary, secondary, or tertiary alkyl halide, because that's the key factor on which reactivity is depending upon. So primary alkyl halide will be most reactive, and then the secondary, and then the tertiary will be the least reactive. So if both molecules have same nature of carbon, that means let's say both molecules have primary carbon, then we will check which carbon has less steric hindrance, because steric hindrance is the key factor. And least steric hindered carbon will react more rapidly through the SN2 mechanism. So we will start checking by first pair. First pair is, the first is bromobutane and second is 2-bromobutane. So they are different just by the position of bromine through which, or to which it is attaching to the carbon. So in the first case, the bromine is attaching with first carbon. In the second case, the bromine is attaching with second carbon. So it is 1-bromobutane, it is 2-bromobutane. due to which the alkyl halides will be different. The first is primary because bromine is attaching with the carbon which is attaching with one other carbon, while in the second pair bromine is attaching with the carbon which is attaching with two other carbons, so it is a secondary. Okay, so you can clearly say that order of reactivity of SN2 is primary highest, then secondary, then tertiary. So 2 bromobutane, which is a secondary alkyl halide, and 1 bromobutane, which is a primary alkyl halide. So the approach of nucleophile is more hindered in the 2 bromobutane because it is secondary than in the 1 bromobutane. So your reactivity will be that 1 bromobutane reacts more rapidly than the 2 bromobutane by SN2 following the SN2 mechanism. Now, if you see the second pair where the two structures are given, first is 2 bromobutane and second is 2-bromo-2-methyl propane. This 2-bromobutane is secondary, we just have seen, and this 2-bromo-2-methyl propane is tertiary because bromine, the halogen, is attaching with the carbon which is attaching with other 3 carbons. So this is a tertiary alkyl halide. And you know that reactivity order of SN2 is highest for primary, then for secondary, and least for tertiary alkyl halides, right? 2-bromobutane is secondary alkyl halide, 2-bromo-2-methyl propane is tertiary alkyl halide. So, greater number of substituents are present in the tertiary alkyl halide which will offer the steric hindrance then in the secondary alkyl halide to hinder the approaching nucleophile. So, more steric hindrance will be present in the tertiary alkyl halide. So, that's why 2-bromobutane, which is secondary, will react more rapidly than the 2-bromo-2-methyl propane by the SN2 mechanism. Now, let's see your third pair. Your third pair is, first is 1-bromo-3-methyl-butane, which is your primary structure, and another is 1-bromo-2-methyl-butane, which is again a primary structure. Okay, so we have similar alkyl halides, primary and primary. Now, the order of reactivity of SN2, you know, highest for primary, then for secondary, then for tertiary. But in this case, we have both the molecule as primary alkyl halide. So both alkyl halides are primary. So substituent, which is methyl, is at a greater distance to the carbon atom linked to bromine in 1-bromo-3-methyl-butane comparatively to 1-bromo-2-methyl-butane. The methyl group, which is a substituent present at greater distance from the bromine substituted carbon in the 1-bromo-3-methyl-butane comparative to 1-bromo-2-methyl-butane. Here the distance are closer. So steric hindrance will be the approaching nucleophile is less hindered in the case of 1-bromo-3-methyl-butane than in the case of 1-bromo-2-methyl-butane. So your 1-bromo-3-methyl-butane will react faster than the 1-bromo-2-methyl-butane by the SN2 mechanism due to the presence of lesser steric hindrance in the 1-bromo-3-methyl-butane. Okay, let's see the summary that we have covered today. First of all, aryl halides are lesser reactive towards the nucleophilic substitution reactions. The reason is, first is resonance effect we have seen due to which the reactivity decreases. Then we have seen the difference in the hybridization of carbon in the carbon-halogen bond in haloarenes. Then we have seen the instability of phenyl carbocation forming after the removal of halogen from the carbon. And also the fourth factor is repulsion, which is the responsible factor for the lesser reactivity towards nucleophilic substitution reaction of haloarenes. Nucleophilic substitution reaction may be possible under high pressure and temperature, which is known as Dawes process. And the use for the conversion of chlorobenzene to phenol under harsh condition. Dawes process we use for the conversion of chlorobenzene to phenol under the harsh conditions. Electron withdrawing group, if present on the benzene ring, will increase the reactivity of haloarenes towards nucleophilic substitution reaction when it is attached at particular ortho and para positions only. Okay, due to its nature of electron withdrawing. Okay, it will withdraw the electron of benzene ring and make it more available for the attack of electron-rich nucleophile. So if you see this reaction, we have seen nitro group is present at para position, and you can like this reaction is taking place at comparatively lesser temperature from the DOS process. No effect on reactivity towards the nucleophilic substitution reactions observed when there is electron withdrawing group, but it is attached at the meta position, because the carbon ion forming and the negative charge coming will not localizing on the meta carbon. That's why even when electron withdrawing group is present in our benzene but it is attaching with the meta carbon, it will not show any effect towards the reactivity of haloarenes towards nucleophilic substitution reaction. Okay, thank you so much. That's all for today's chemistry session. Thank you.